Okay, so today we're going to make a foldable to summarize what we've learned about the different gas laws. So we're going to start with a piece of paper. You can use either computer paper or notebook paper. It doesn't matter which. I just happen to have computer paper handy. You're going to start by folding it in half, vertically, hot dog style, the long way, long and skinny, whatever you want to call it. I don't really know all the verbiage here. Then you're going to fold it in half again the other direction. And in the same direction that you just made that fold, you're going to do it one more time. Then we're going to unfold this part, and you're going to cut along each of your folds just to the center fold on one half of it. So when you're done, you should have 4 little flappy doos. Okay, so that's how we make the foldable. The first law we're going to talk about is the first one we studied in the instructions, Boyle's Law, which, if you recall from the instruction video, is the relationship between pressure and volume. We have P1 times V1, our initial pressure and our initial volume, is equal to our final pressure times our final volume. And the important thing to remember here is that we are holding temperature and the number of moles of gas constant. So that's not changing. So let's go ahead and open up our foldable. There are 2 ways that we can say this next word. We can either say that these 2 variables are inversely proportional, or we can simply call this an inverse relationship. Okay, what that means when we say something is inversely proportional or that it has an inverse relationship is that as one variable goes up, the other variable goes down. So if my pressure is becoming greater, then my volume is getting smaller. If my volume is getting greater, then my pressure is getting smaller. Okay? Now, when we take some data and actually graph this relationship, so draw yourself a little graph. You only want to take about half of this because we're going to do something on this other half. So if we have a graph of volume on the X versus pressure on the Y, we're going to end up with a curve, not a line, a curve. So this is nonlinear, but it is going to be a curve that is going down and to the right. Okay? Because as the volume is increasing, the pressure is decreasing. Okay? So let's put this in a visual. Let's say that I had a balloon, a nice big party balloon. Okay? And let's just use real simple numbers. Let's give this a volume of 1 and a pressure of 1. Okay? If I have that same balloon with the same amount of gas in it, but it is only half as big, so my volume is 0.5, half as big, then my pressure is going to be twice as big, or 2. Because if I take that same amount of gas and I push it closer together into a smaller container, I'm going to end up having a lot more collisions. And those collisions with each other, with the container, are what make up the pressure of the gas. The next law we're going to look at is the second one from the instruction video. It's called Charles's law. And Charles's law is a little different from Boyle's law. Here we are holding pressure and the number of moles of gas constant, and we're looking at the relationship between volume and temperature. And you'll notice Boyle's law, we were multiplying on both sides. Charles's law is different. Here we are dividing on both sides. So we have our initial volume divided by our initial temperature is going to be equal to our final volume divided by our final temperature. And just remember, T must be in Kelvin. So when you're doing calculations, always make sure that that T value is in kelvins. To get from Celsius to kelvins, remember you add 273.15. Now, you'll notice that the equations are different. We're doing a different operation because the relationship is different. For Boyle's law, we said it was inversely proportional, or an inverse relationship. For Charles's law, it is not inversely proportional. This is called directly proportional. Or you could simply call this a direct relationship. Now, a direct relationship is really quite the opposite of an inverse. With inverse, when one goes up, the other goes down. With a direct relationship, as one variable goes up, the other variable also goes up. And here's the key, really important idea, at the same rate. So what do I mean by that? If I double the temperature, it's going to double the volume. If I cut the volume in half, it's going to cut the temperature in half. They're going to change at the same rate. So if I were to draw a graph, remember that the inverse graph looked a little different here. It's a curve that goes down and to the right. This is not going to do that because this is a different relationship. So if we're graphing temperature versus volume, this is going to be a linear relationship, not a curve, and it's going to go up and to the right. Okay? Because as one increases, the other increases. So as my temperature goes up, my volume is going to go up too. All right? So to put this in visual terms, if I have a balloon, and my balloon is at a temperature of 273 Kelvin, and the volume is 1 liter. Let's say that keeping the pressure and the amount of gas in there the same, I were to heat this balloon up until the temperature was twice as big. So we have twice as much temperature. I'm sure you can all visualize that that's going to make the balloon bigger. So twice the temperature would be 546 Kelvin. But what you want to notice here is that the volume would also exactly double. If we exactly double the temperature, it's going to exactly double the volume. So this would have a volume of 2. All right? Our third law that we're going to look at is Gay-Lussac's law. Okay, and in Gay-Lussac's law, we are going to hold volume and the number of moles of gas constant and look at the relationship between pressure and temperature. And I think you're going to recognize this equation as being very similar to one of the other two. Gay-Lussac's law is P1 over T1 is equal to P2 over T2. That looks an awful lot like Charles's law, except for instead of volume, we're looking at pressure. But mathematically speaking, the relationship is the same. And again, remember that your temperature must still be in Kelvin. For all of these calculations in this unit, we always want our temperature in Kelvin. Okay? So Gay-Lussac's law, because the equation is the same in terms of the relationship, we're dividing in both of them, this is also considered a directly proportional relationship. Or you could simply call this a direct relationship. So you would say, just like we did with Charles's law, that as one variable goes up, the other variable goes up. And again, really important, at the same rate. Okay, so if I double the pressure, it's going to double the temperature. If I double the temperature, it's going to double the pressure. If I cut the temperature in half, it's going to cut the pressure in half. All right, so the graph for Gay-Lussac's law is going to look really similar to the graph of Charles's law. The only thing that's going to be different is the labels for the axes. This time, instead of temperature versus volume, we're doing temperature versus pressure. But the relationship is the same, so the graph will look the same. It's going to be a linear graph, nice straight line, going up and to the right. Because as the temperature increases, the pressure increases. Okay, so now here we are holding the volume constant. It's not changing. So here, and I'm going to do my very best to draw this correctly, my balloons are going to be the exact same size, same volume. They're not perfect, but they're pretty close. Give me credit there. All right, so if I have a temperature on this first one of 273 and a pressure of, let's call it 1 atmosphere, if I increase the temperature, let's say I double it like we did before, and it becomes 546 Kelvin. Well, the balloon isn't getting any bigger, so what's happening, excuse me, to the pressure inside the balloon? Think about that. If we give all those little gas particles a whole bunch more kinetic energy, but they can't expand, they can't get any bigger, they're going to start running into each other a lot more. And so it's going to create a whole bunch of collisions, specifically twice as many collisions. So this would have a pressure of 2 atmospheres. And then the last scientist law that we need to talk about is Dalton's law of partial pressures. Okay. With Dalton's law of partial pressures, we have the final total pressure of all the mixture of gas. And that total pressure is going to be equal to the partial pressures of each of the gases that make it up. So the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and we keep doing that until we have accounted for every single gas. Now, this particular one, we can't really call it an inverse or a direct relationship because we're not comparing it to another variable. The only variable in this equation is pressure. Okay? We're just looking at pieces of a total. So I'm going to show you an example over here of one of the most common things that we do. And y'all have already done this in one of our labs this year, where we collect a gas over water. So do y'all remember the lab where we had a bin and it was filled? I'm a terrible artist, so forgive me. The bin was filled with water, okay? Bin full of water. And what we did is we took a test tube and we sunk it down into the water so that the test tube was filled with water. And then we stuck the test tube face down in the water, filled with water, all the way to the tippy top, filled with water. Then we ran a gas hose little rubber tube into our reaction. And inside our reaction, we had some zinc that we were dissolving in hydrochloric acid. And this resulted in gas bubbles. So we had gas bubbles that were going up into the tube and up into our test tube. And as the gas collected in the test tube, the water level started to go down. Okay? And we kept doing this until the test tube was full of nothing but that hydrogen gas. Or was it? Now, here's the thing. Anytime we have a liquid like this water down here, there are always particles of water in the gas phase just above it. Because if you remember how the water cycle works, water is condensing and evaporating at the same time in this kind of pretty little equilibrium, okay? And you know that if I were to take a glass of water and leave it sitting out for weeks on end, eventually all of the water in that glass would evaporate. So we know that even though we have our liquid water sitting here, there's also water in the gas phase above it. And it turns out that the warmer the water is, the more water in the gas phase there is above it, okay? And so we have this concept of the partial pressure of water. And the partial pressure of water at any given temperature can be looked up on a chart. This is a known value type thing. So we can actually go to this little chart and say, oh, my water is 23 degrees Celsius and the partial pressure of water at 23 degrees Celsius is this. And we can use that value. And that allows us to say, okay, if my total pressure is this, what would the pressure of my hydrogen gas be? So in this kind of a setup, we know the partial pressure of water. We can look this up. And it is based on temperature. The total pressure of the gas can be measured. We can use a device to measure the pressure inside our test tube. And with those two pieces of knowledge and Dalton's law of partial pressures, we can calculate the partial pressure of our hydrogen gas in the tube. So let's look at an example problem like that.